This video contains a short introduction to how we can use Schrödinger and the Jaguar program in Schrödinger in order to perform calculation of vibrational frequencies of molecules. So we will illustrate it for a molecule like cyclopropane. So I will just choose this molecule and put it in the workspace. And as always, I like better a representation where we can more clearly see the atoms here. The first thing I do is that I go to the workspace and I create a project entry. I will just call it Psych in this place here. So let me create this. After this, I take the application, I go to Jaguar and I do optimization. Now on this line here, the molecule appears and it has been assigned a charge of 0, a spin multiplicity of 1 and a default 631G ** basis set. So let's just keep it like this. Under theory, I can choose DFT, Hartree-Fock and MP2. Hartree-Fock is the fastest, so let's use this in order just to illustrate the method. Under properties, I click on vibrational frequencies, and if I want a solvent model included, then I can here from the list choose, for example, PBF, which is a Poisson-Boltzmann solvent model with default assigned water molecules as the solvent. But in this case, I will not include any effects of solvent. So let me try to run the calculation. It takes a half a minute or so, would my guess be. I can see that now when I have submitted the calculation, this button here turns green. By pushing at this, I can see that the job is running, and if I want, I can go and monitor the progress of the job by clicking on the output file here. So what the program does now is that it performs a geometry optimization of this molecule here, meaning that it puts the atoms at the most favorable places, simply in order for the energy to be at minimum. After this geometry optimization has been performed, and we can scroll up to this point here, geometry optimization complete, the program now initiates a calculation of the vibrational frequencies. The result of this is a list of vibrational frequencies. We can see the frequencies here, 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 here. We have 3n minus 6, where n is the number of nuclei in this case here. And we can also see what the intensities are related to these vibrational frequencies here. The vector down here is the normal coordinate associated with the given vibrational frequency. So this calculation here terminated normally. Let's close this dialog box here and let's go and open the table. Now in the table I have now a line here called Psych, which is the result of my calculation. I can click on the small blue V, and then I again get the list of vibrational frequencies here and the associated intensities here. I can now begin and animate those different vibrational frequencies, and by clicking at them here I can assign if these correspond to, for example, a bending of the ring or a stretching of different bonds in the molecule. So by this I can animate my vibrational frequencies. But let me close this dialog box again here. The last thing I can do is from the applications, I can choose Jaguar. I can go to the button where I have plot spectra. Now this will give me something looking like this. Now I want to plot a IR spectrum here, and now I need to select which entry I should do it for. Well, my calculation was called Jaguar 32, so if I go into this folder, I have a file here called Jaguar 32vib. So if I double click on this, then I get the vibrational spectrum out like this. And in addition to this, I have the list of frequencies and the associated intensities. Now what can be done here is that one can manipulate with this structure here, and by performing such structural manipulations we can directly the relation between structure and vibrational frequencies and the appearance of the IR spectrum, meaning that we can use this way of using computational methods here to do structural assignments of our molecules.